Hello
Hello
everyone.
everyone.
Thank you
Thank you
for
for
joining me
today.
I'm excited to talk about my topic
on
virtualization GPU with SR-IOV on the yeah. So at first I want to apologize for not being there in person due to unexpected visa issue. I wasn't able to travel to the US. So I'm disappointed. But I'm still grateful to be able to present remotely. Yes. We have just heard a great presentation on PCIe pass-through on ARM from Stewart yesterday, which is a fantastic foundation for our discussion. My talk builds on that concept by focus on especially on the GPU design by Jingjia Micro, a China local GPU design. Where traditional pass-through give a single virtual machine inclusive access to a device. SR-IOV allows us to slice up a single physical GPU and share it among multiple virtual machines. That's a game changer for the GPU virtualization. So over the next few minutes, I'll first explore why high-density GPU virtualization remains an important and challenging topic today. Then I will explain our reason for choosing SR-IOV as our core technology. After that, we'll take a deep dive into the overall architecture on this. Yes. Spirit how we virtualize the core GPU units and the key role played by the customer and driver. So why are we doing this? Because the demand for virtualized GPU resource is growing from VDI, which requires a smooth desktop experience for every user. And to cloud gaming and media services, the one powerful encoding for each concurrent stream. Yes. The core challenge is how to maximize the number of users a single physical GPU can support without sacrificing performance or feature. To solve this problem, we involved existing technologies. Traditional method like API forwarding, while flexible, come with significant CPU overhead and incompatibility problems. On the other hand, device pass-through were offering this lead us to choose SR-IOV. Yes. It allows to partition a single GPU, which we call a PF into multiple lightweight VF. And each VF can be directly assigned to a virtual machine. The advantages are clear. It provides native performance, security isolation, and excellent scalabilities. So now let's see how this all come together in the architecture is built on a physical GPU with SR-IOV capabilities. With those have many rings on a line CPU and memory isolation. So critical part happens in domain 0. We run a custom the driver in domain 0 responsible for initialize the GPU. It enables the SRV and creating VF when we need. But once the VF are created, how do we securely pass them to the gather VM, the gather domains? This is where a very important is a very important framework in the Linux kernel comes. The VFO PCI or PF driver utilize VFO PCI and unbound this newly created VF from the domain 0 kernel driver and expose them safely to user space. From there, the Xen to a stack can assign a VF to a specific domain. From the domain gather domain perspective, the VF appears as a real physical PCIe device, allowing it to load standard vendor drivers. More importantly, VFO PCI is tightly integrated with the LMU, with provided hardware level isolation. Yes, this ensures that no virtual machine can access memory that doesn't belong to it. Yes, so let's start with how we implement the how this was done. It was divided into 3 steps. First, the PCIe configuration, space virtualization. This is where SRV comes into play. Yes, the hypervisor role is simply but critical. It handles the initial setup and configuration of the PF to create and expose this VF, and essentially preparing the GPU for sharing. So with the virtual interface created, we move to the second step, backend computing resource partition. This is the process of dividing the physical GPU actual hardware resource, the process core, or the render clusters, and the memory, the frame buffer, and the VPU into isolated partition. We need to be able to logically carve out sections of that blocks of each VM. The partition is essential. And the last step, and also most critical step, is association of the VF with the backend resource. This is a magical part where we link the virtualized front end, the VF, that we send to the virtual machine with the partitioned backend resource. This is handled by the network on-chip hardware. This ensuring that when a virtual machine sends a command to its assigned VF, the command is correctly routed its isolated partition of the GPU's physical resource. So in essential, we are not just giving a virtual machine a vGPU. we are giving it its own dedicated slice of the physical GPU power, or we are ensuring that other virtual machines on the same host can do the same without getting in each other's way. So with the most important, how do we partition the GPU subunits? We can break them down into 4 main categories. First, the frame buffer. The frame buffer is the GPU's memory. When we share the GPU, each VM is assigned a dedicated portion of an on-chip DDR for its own frame buffer. This ensures that one virtual machine display data is completely isolated and cannot be accessed by another. So it providing both performance and security. Second is the rendering units, like the 3-dimensional units, and they are the curve processing clusters responsible for rendering graphics. The unit can be divided and assigned to VFs. For example, a single vGPU with multi render clusters can be partied. Give each virtual machine a dedicated cluster or a set of clusters. This is crucial aspect of providing performance isolation for graphics workload. Now, the third, the VPU, it handles the video encoding and decoding. Unlike the render units, which can be partied, the VPU is often a shared resource. So we manage this sharing using the time slicing, where the VPU is scheduled to process tasks from different VFs is a rapid succession. We are not offering the same level of performance isolation as a dedicated resource. It allows multi-virtual machine to use the same VPU efficiently. The last one is the super sampling. Similar to NVIDIA DLSS and AMD FSR, providing high performance such as high FPS and resolution. They are designed for specific high performance tasks and cannot be partied. So because they cannot be divided, they are only available when a VF has been allocated the entire GPU resource in a shared scenario. These units are typically not accessible. Now, we can focus on the driver, or we can call it it runs in the domain 0 and is the brain of the operation. It has 4 key responsibilities that ensure the smooth and safe operation of our shared GPU environment. First, initialization. The first job is to get to know the physical GPU. It probes the hardware and understand its capabilities and enable SR-IOV. Second, we do the resource allocation. When the VF are up and running, the driver takes on the role of a resource manager. It handles differentiate vGPU profiles, allowing us to allocate a resource based on the VM specific needs. For example, a VM runs a high-end design application. It has a large vGPU profile, so we assign more clusters. Then the VM use for user-led office task to ensure fair and efficient resource utilization. And the third, arbitration. Yes, a major challenge is sharing a single device is managing the access to share resource and prevent one VM from causing problem for others, such as the VPU. So the driver acts as an arbitrator, safely managing access to share registers to prevent bucket gets the driver from disrupting the physical function. The last, the error containment. Finally, the driver provides a critical layer of error containment. If a get driver within a virtual machine crashes, our driver is designed to detect this and reset only the affected VF. This is the powerful safety feature. It ensures that the physical function and all the other VFs on the GPU continue to operate without interruption. Oh. Now we can talk about some of the problems we faced. The first problem we face is how to prevent a single virtual machine fails from causing a cascade effect that could disrupt other users or services. The solution is the function level reset. Yes. When a virtual machine crashes or specific application with the machine fails, the virtualization layer can trigger a function level reset for the affected VF. The reset touches only the resource associated with that specific VF. It clear is state and flash is buffer. This process doesn't affect the operation of other VF or other PF. The second problem is how do we do the dynamic partition? Yes. In many user cases, different virtual machines, they use different kind of resource, and we define a different kind of vGPU profile. We list 4, and the different profile, so different kind of vGPU can coexist on the same PF. It allows the amount of backend computing resources associated with a specific VF, and it can be changed. And another problem we should to solve is how the guest OS to communicate with the host, and the host also should communicate with the guest. First, we talk about the host communicate to the guest, the DOM 0 to the guest domain. Yes. When a vGPU is assigned, DOM 0 reads the vGPU's type and its resource location, such as the memory size, the number of cores, the number of clusters into a shared memory, in a shared memory area. The guest driver in the guest domain reads this information, allow it to correctly initialize the vGPU, and regardless of whether it's a full pass-through or a partitioned vGPU, this ensures driver universality. And the second case, the guest domain have information to the domain 0. The guest driver in the guest domain continuously writes its resource usage data, such as the GPU utilization and the memory consumptions, to the shared memory region. And the DOM 0 virtualization driver reads this data and enable it to monitor and manage the vGPU environment. ensuring fair resource distributions and identifying potential bottlenecks. So that's we have success. We did this. We give a high-dense vGPU virtualization solution on them and support up to 32 vGPUs in our demo in our development environment, and get fine-grained resource sharing across all major GPU subunits and use the SR-IOV model. And the future roadmaps, we want to do the level migration, and also want to broaden our hardware support, such as the ARM server. Yes, so that's all.
Thank you, Linwen.
Okay, so I told my
Let me see if there's any questions.
So if there are no questions, I stole my share.
Hi, can you hear me?
Yes.
I just was wondering, what's the status of the implementation?
Now in our environment, we have done this implement, and we have a complete full driver, and it can run in the physical GPU in our we call it a Jingjia 11 GPU. It can support 32 virtual machine.
The follow-up. Is there somewhere where we can access the code for this to try it out ourselves?
Now it was not open right now, but I'm trying to pursue this and try to work with the community.
Great if you could do that, because we're trying to do the same thing.
Okay. We also, you can connect me, use the email, and we can also communicate.
Yep, I'll do that. Thank you.
Linwen, you have two questions in the chat. First one is, what hardware is supported right now?
So hardware is is from our company, is Jingjia 11. We call it Jingjia 11. So the window code, yes, it was only available in China.
Here's a second question. Does a PF driver crash in DOM 0 need a reset of all VFs?
Yes, but the PF driver is rising. So the function, most of the functions are done in the hardware.
So each vGPU has a frame buffer, but how is this frame buffer exposed to the users?
The frame buffer is associated. The frame buffer is associated with the VF. We did this by the on-chip network hardware. It connects the PCIe VF to the backend DDR controller, and it can allow the specific PCIe VF to access a specific DDR controller.
Sorry, just a question I didn't understand. So this approach applies on every SR-IOV capable GPU, or just some special hardware you have?
Is for those specific hardware. Yes, this design is should get
design the
support
hardware
from
to go with your drivers. Okay.
Yes.